Okay, so the first part, first two sections introduce the ideas of radioactivity, and those are great things to read, but mostly people understand those okay. So I'm going to talk about the types of radioactivity here, and then we're also going to talk about the valley of stability. So, of course, Marie Curie was instrumental in discovering radioactivity. Rutherford studied it as well. So the essence of radioactivity is that the nuclei of radioactive elements are unstable and spontaneously decompose, emitting small pieces of themselves to gain stability. And there are different categories of natural radioactivity. These include alpha decay, beta decay, gamma ray emission, positron emission, and electron capture. Those are not necessarily the only ones, but those are the ones we're going to talk about. So we need to review our nuclear symbols. We covered these in 1A, but you may have forgotten. So a nuclear symbol uses the regular chemical symbol for the element, and then to the left of that is a superscript and a subscript. The superscript is the mass number. The subscript is the atomic number. So the atomic number is the number of protons in the nucleus. That's the whole number on the periodic table in the same square with the element symbol. And the mass number is the sum of protons and neutrons in the nucleus of that particular isotope. So all atoms of the same element will have the same atomic number. They all have the same number of protons, but different isotopes can have different mass numbers. If we're interested in finding the number of neutrons, we can take the mass number and subtract the atomic number and get the number of neutrons. So most elements have several different isotopes, and we often refer to a particular isotope as a nuclide. We can represent isotopes by their nuclear symbols. We can also use the element name or symbol followed by the mass number. We can also represent the main subatomic particles with nuclear symbols. So a proton is a lowercase p, its mass number is 1, and its number of protons is 1. A neutron is lowercase n, it has a mass of 1 and no protons. And then there's the electron with an e, a mass of 0, and what seems strange, but we'll realize why, it has the number of protons is -1. So in alpha decay, good place to start since A is the first letter. In alpha decay, an unstable nucleus will emit an alpha particle. That alpha particle, excuse me, the alpha particle is identical to a helium nucleus. So it's got 2 protons and 2 neutrons, but there's no electrons because this is just the nucleus. So we have an unstable nucleus, and spontaneously it spits out this particle containing 2 protons and 2 neutrons. And that's what's known as alpha decay. We can represent nuclear processes such as radioactivity using nuclear equations. And these look kind of messy and complicated, but they're actually quite simple once you see what's going on. So the sum of the atomic numbers on both sides have to be equal. The sum of the mass numbers on both sides must be equal. In nuclear reactions, elements are often changing their identities, and so we're not balancing by number of uranium atoms or anything like that. So here's an example of a nuclear equation for alpha decay. Here we have the parent nuclide. The parent gives off a piece and becomes the daughter. So uranium turns into thorium plus a helium nucleus. Now the mass number of uranium-238 is obviously 238. There's 92 protons, and if we want to know how many neutrons there are, we can just subtract. I should have picked something that I could do in my head, but 238 minus 92, 146. So if we needed to know the neutrons, we could just subtract. So we've got this uranium, and it's going to turn into thorium, because when the alpha particle leaves, it takes 2 protons with it. And so the daughter nuclide now only has 90 protons, and we identify the element by looking at the periodic table and finding which element is number 90. The mass number also changes, it decreases by 4. And so we see that the sum of the mass numbers, 234 plus 4, is equal to 238. 90 plus 2 is equal to 92. Any questions yet? Okay, so this is asking us to write the nuclear equation for the alpha decay of polonium-216. So we do want to have a periodic table available, which I should have thought of ahead. I'll have to dig one up here. So we're going to start here with, just pardon the dog noises in the background. 216 is the mass number for polonium. To find the atomic number, we look on the periodic table. I'll pull one up here. Polonium, where'd you go? There you are. Number 84, right after bismuth. So we look up the atomic number, 84. So this is going to undergo alpha decay. So it's going to emit an alpha particle, and the symbol for an alpha particle is that, because it's the same as a helium nucleus. And so then what we need to do is figure out, well, what's the other number here? Something plus 4 must equal 216. So that's going to be 212. And down here, we need a total of 84. So we have 2, and this one must be 82. And then we go back to our periodic table. And find that 82 is lead. So this is PV. Any questions?
Will we ever have to, you know how like there's some that have like 1, 2, 3s, and 4s? Will we ever have to define that, or is it just the basic element?
I'm not sure what you mean by 1, 2, 3, and 4.
Like lead 2, or...
Oh, those are ions.
Oh, okay.
And so here we're talking about atoms.
So, okay, so it's just the atoms, not ions.
Yeah. In nuclear chemistry, we mostly ignore electrons, except when they freakishly come out of the nucleus. More about that later. So a little bit about alpha decay. We often use the analogy of vehicles to help us understand the characteristics of the different types of radiation. So in terms of vehicles, alpha radiation is like an 18-wheeler truck. It's really big. It's massive. So it's the most massive particle that's eliminated by radioactive nuclei. And it has the highest ionizing power. So ionizing power is the ability of radiation to ionize other molecules. So they can knock electrons off or possibly give electrons to other molecules. And in a living organism, this can cause a lot of havoc. If you've got things that are supposed to be neutral molecules and suddenly they become ions, then they're going to behave differently, and your carefully balanced system is going to get messed up. So this can cause cells to die or to reproduce abnormally, which we usually refer to as cancer. So ionizing power is kind of like, the amount of damage that it can do. And so you think about an 18-wheeler truck plowing into a brick wall is probably just going to blow the wall to smithereens. The other thing we think about is penetrating power. So penetrating power, I think is maybe in the next slide. Yeah. Is the ability of radiation to penetrate matter. So in order for radiation to damage important molecules inside living cells, the radiation has to get into the cell. Alpha particles are very large, and they have a hard time getting into the molecule because they're so big. And so here we think about a traffic jam. And if you're driving a semi-truck in a traffic jam, you're just going to have to tough it out and go slow and get through with everybody else, right? You can't weave in and out or go over on the shoulder like you could if you were on a motorcycle or something. You're just kind of stuck. So the alpha particle gets stuck easily. It gets stopped. It can be stopped by something as small as a sheet of paper, t-shirt, even a layer of air. So alpha particles are relatively safe or harmless outside your body, but if you inhale them or you ingest them, now your skin is not stopping them anymore, and then you're going to have a lot of trouble because they ionize things a lot. Any questions yet? So the second type of radioactive decay is called beta decay. And here we have an unstable nucleus that emits an electron. Does that bother you? That an electron comes out of a nucleus?
Yes.
Yeah, that shouldn't happen. There shouldn't be electrons in the nucleus, right? So what happens here is a neutron turns into a proton and an electron. The electron gets spit out and the proton stays. So we can write that equation like this. A neutron becomes a proton plus an electron. So we can write beta decay equation for radium-228. It's giving off an electron, and then this is the result. So the reason that we have the proton number okay. Oh my goodness. So we have two dogs. I have a female Belgian Malinois who is currently in season. She's a little over a year old, and she's about 45 pounds. And then we have a little Pomchi. He's about 10 pounds, about the size of a cat. And he's neutered, but he's a male. And so they have been going at it for 2 days now, and that's what all the heavy breathing in the background was. It wasn't that they were physically warm. It's the male dog being really excited, and he's got this crazy look, and he does this thing with his ears. So, and he's humping her leg because he's so short. He can't get anywhere close to where he's supposed to be. So, my husband just handed me a note. Churro's an alpha particle, no penetrating power.
Beta particle. Oh yeah, alpha particle. Yeah. That's what I meant.
Oh, and it busted me up. Oh, I live in a circus. And then we've got the two kittens that are just so fun, but we have to worry about the dog chasing. Anyway, it's just been really, really interesting. Okay, I think, yeah, they've left the room, so maybe I can focus. So back to the business of an electron coming out of a nucleus. So the reason that the electron has a -1 atomic number is because when the electron leaves, the atomic number goes up because now we have another proton. The neutron turned into a proton and an electron. So in this sort of decay, the atomic number actually increases. The mass number stays the same. And here we have another illustration. Yes?
Can you say that again? That when the electron leaves.
Yeah, when an electron is emitted from the nucleus, this is not one of the regular electrons. Now this whole chapter is about nuclear chemistry, and so this is all the things that we said except for in Chem 1A. You know, conservation of mass except in nuclear reactions. So now we're getting to all the weird things. So a neutron, and I understand if this is hard to swallow, a neutron can break apart into a proton and an electron. The proton stays in the nucleus, the electron leaves. And so now we have one more proton in the nucleus than we had before, so the atomic number goes up. The electron has essentially no mass, and so the mass number stays the same. We have the same number of protons and neutrons, but one of the neutrons has turned into a proton. So if we look at this, 228 minus 88 is 140. So 140 neutrons and 88 protons. Over here, we're going to have 139 neutrons and 89 protons. So a neutron has turned into a proton. Of course, a neutron and a proton are not identical, and so when that happens, an electron is formed. It's very strange.
But didn't the neutron just turn into the... Oh, wait,
Turned into the proton. Mm-hmm.
Never mind, I was reading that wrong.
Yeah, it's very weird. So, in terms of vehicles, beta radiation is like a 4-door sedan. Good-sized car, right? Beta particles are less massive than alpha particles, so when they run into things, they don't do as much damage, so they have lower ionizing power. But they have higher penetrating power than alpha particles. So just like in a traffic jam, a car can change lanes and get through a little easier than a 18-wheeler. The beta particle can get through matter more easily than alpha particles can. So beta radiation can be stopped by a sheet of metal or a thick piece of wood, but paper or clothing is not going to stop it. So beta radiation is more dangerous outside your body because it can get in, but it does less damage if you ingest it or inhale it.
Now, when you say ingest or inhale, how exactly do you inhale?
Well, so have you heard of radon gas?
Oh, yeah.
Radon is a radioactive gas that seeps into people's basements in certain parts of the country. And then you would inhale that, and now it's in your lungs.
Okay.
Yeah.
So it has to be it has to be combined with like in a gaseous state.
It would have to be, yeah, in a gas state.
Okay, all right. That makes sense.
Or, eating it could be all kinds of things. So the third form we'll talk about is gamma ray emission. And as the name suggests, these are rays, not particles. It's a form of electromagnetic radiation. If you remember from Chem 1A, at the high energy end of the electromagnetic spectrum is gamma rays. So they are high energy photons. The gamma ray has no charge, no mass, and so when a gamma ray is emitted, the mass number and the atomic number of the element do not change. We usually see the gamma rays are emitted along with another type of radiation. So the symbol for a gamma ray is the letter gamma and 00 because its mass and atomic number are 0. So here's an example of gamma radiation. Here we've got uranium-238 undergoing alpha emission, alpha decay, and along with the alpha particle, a gamma ray is also emitted. So gamma rays are like the motorbikes or motorcycles of radioactivity. So they have the lowest ionizing power. When they smash into molecules, they don't ionize them very much, but they have the highest penetrating power. So in a traffic jam, you've probably observed this sometimes, people on motorcycles will sometimes drive between the rows of stopped cars, and so they can get through. So gamma rays can get through lots of things. In order to stop them, you'd need several inches of lead shielding or thick slabs of concrete. Anything less and they just go right through. Another type of radiation is positron. So the name positron kind of sounds like electron, and a positron is like an anti-electron. It's the antiparticle of the electron. It has the same mass but the opposite charge, and if a positron and an electron collide with each other, the two particles annihilate each other and they release energy in the form of gamma rays. So when we have positron emission, we have a proton being converted into a neutron and a positron. And if that sounds a little familiar, that's because we were talking about a neutron being turned into a proton and an electron. Proton can be turned into a neutron and a positron. And so we can write an equation for that as well. So the symbol for the positron is like the electron, but with a +1 instead of a -1. So if an atom emits a positron, the atomic number decreases by 1 because you've turned a proton into a neutron. So you can have phosphorus 30 becoming silicon 30, positron being emitted. Positrons are similar to beta particles to electrons in their ionizing power and penetrating power. Questions? Another type of radioactivity is called electron capture. And this is when a particle gets absorbed by the nucleus instead of being emitted, as the name capture suggests. So a nucleus captures an electron, it assimilates an electron, and that electron is coming from an inner orbital of its electron cloud. There's thumping and bumping out there, but it stopped. So the net effect of this electron being absorbed is that the proton gets turned into a neutron. So this is the exact opposite equation of the beta emission. Here what we have is the atomic number decreasing by 1, mass number staying the same. Because in the process of electron capture, we're turning a proton into a neutron. So So here's a table that summarizes these different types of radiation. And there's really not much to say about that. So, what should we be able to do? We should be able to write nuclear equations. So write 3 nuclear equations to represent the nuclear decay sequence that begins with the alpha decay of U-235, followed by a beta decay of the daughter nuclide, and then another alpha decay. So I'm going to start this out by writing the nuclear symbol for uranium-235. That notation doesn't give the atomic number, but that's okay because no chemist should be further than arm's reach from a periodic table. Where'd you go? Left my glasses in the other room. 92. So uranium-235 has 92 protons. And the formatting's messed up here. Begins with alpha decay. So for alpha decay, I'm not sure why they always write the nuclide first, the daughter, and then the decay. So there's the symbol for the alpha particle. And then we are going to fill in the blanks, essentially, for the numbers here. So we know that the total of the superscripts on the right has to equal the superscript on the left. So we must have 231 here. 231 plus 4 equals 235. And then in the bottom, we need 90. And then we look that up. Good grief, where'd you go?
Thorium.
Yes, thank you. Thorium. So that's alpha decay of uranium-235. And then it says, followed by a beta decay of the daughter nuclide. So this is the daughter nuclide of the first one. So we're going to take this, and we're told that it undergoes beta decay. So that's the emission of an electron. And then to find the superscript here, what plus 0 is 231? And what minus 1 is 90? So this must be 91. And that's PA. So we did the first alpha decay, did the beta decay, and then it says followed by another alpha decay. So again, we're going to take this daughter here, 231, 91, PA, goes to something plus an alpha particle. Four plus what is 231. Now, this kind of math you should be able to do in your head, but it's dumb to get it wrong on a test. You can use your calculator, it's okay. And here, 2 plus what is 91. It'll be 89. Look on a periodic table, 89 is AC. And you probably don't know the names of those elements, and that's okay. You can do the equations without knowing what their names are. Any questions?
Will we always start with the daughter when we're doing a progression like this? Or is it just because of this problem that we are always starting with the daughter?
You'll almost always start with the daughter. Because after this atom has decayed, this atom doesn't exist anymore. So all that we've got then is this. And so this undergoes decay to form this. This doesn't exist anymore. And so that's how it goes. Excuse me. Hey, baby. Yes, I love you too. Yeah. Oh. All right. You're going to be here? No, don't eat that. I don't think this is good for you. Okay. Any questions? This one's saying, write the nuclear equation for the positron emission of sodium-22. So sodium-22, and then we'll look up the atomic number for sodium. And this is going to emit a positron. So the positron is like an electron, but a positive charge. And then for this daughter, we're going to just do some simple math with the superscripts and the subscripts. So this must still be 22, and the bottom must be 10. Because 10 plus 1 equals 11, 22 plus 0 equals 22. And then we look up element number 10. And we got neon. Now, in a face-to-face class where you take exams in class, you have to memorize the symbols for these different particles. At home exam, you can look in your book, but you'll be able to do this much faster if you're just checking yourself instead of looking up how to do the whole thing during the exam. Write the nuclear equation for electron capture in krypton 76. So krypton 76, element number 36. And then this is one that I kind of have a hard time remembering. I was wondering if it's nicely shown in the back of the book, but they don't. So this chart is helpful. Electron, now I forgot what I was doing. Was I doing electron capture?
Yes.
Yeah, okay. I don't know. So, electron capture, and a brain fart, it's not that hard to remember. We're just capturing an electron. And again, we're adding up the numbers. So this time we have two things on the left, 76 plus 0, 76.
Oh, that's plus.
36 and negative 1, 35. Find element number 35. I think this bromine.
So when we're talking about the positron emission and the electron capture, we're going from the daughter to, is that like technically, would that be considered the daughter?
That's an excellent question. I think that would still be considered the daughter because it comes after. It's
Okay.
produced by, even though it's, because sometimes the daughter is actually more massive than the parent.
Mm-hmm.
And will a electron capture always be written with the two elements and then going to the third element?
Yeah, because capture means you're adding an electron. Yep.
That's the only one that where the particle is absorbed, right?
Right, that's the only one we're going to talk about.
Okay.
Come on, mouse.